Today we're starting Chapter 4, and we're starting with Section 4.1, talking about polynomial functions. And a polynomial function of degree n is a function that has this form, and you can see it there, p of x, which p they just use for a generic polynomial. And it's a sub n times x to the nth power plus a sub n minus 1 times x to the n minus first power plus, and then you got those dots there, and then plus a sub 1x plus a sub 0, where n is a non-negative integer. And the biggest thing that people need to understand when they see this is simply that all of those a values are numbers. So when you see a sub n minus 1, a sub n, a sub n minus 1, a sub 1, a sub 0, all of those are simply constants. They're simply numbers. And then x to the nth power, this is just whatever power, some power, and then this is a power 1 less, and then a power 1 less, and 1 less. So all these things that we've done so far, like quadratics, are polynomials. You know, for example, 3x squared plus 2x minus 1, that is an example of a polynomial in this form. You just have numbers. That'd be a sub 2, a sub 1, a sub 0, and then you have a power of 2 and a power of 1 and then a constant. So that's all this is, and it's just because we don't know how many terms this polynomial has. That's why we have to write it in this way. So the numbers a sub 0, a sub 1, all the way up to a sub n are called coefficients, and again, they're just numbers. A sub 0 is called the constant term because it does not have a variable with it. And then a sub n is called the leading coefficient. Again, leading because it is the first one. It's the one at the very beginning. Finally, the polynomial with just a single term is called a monomial. Mono meaning one, so single term, monomial. So now as we look at a summary of the different graph types, we're going to kind of see some patterns here. The first one is a linear, y equals x, and that x is raised to the first power. And we've seen those before, that's just a line. When we raise y equals x raised to the second power, and again we've seen this before, this is a parabola. Y equals x cubed, it's kind of an S shape, an S curve, but notice all these so far have gone through the point 0, 0, and this one, if you look at it, actually goes through the point 1, 1, right here, and right here, and negative 1, negative 1, those 2 points, just like a line did. If you remember, x to the first power went right through there. So that's kind of an interesting fact. Then we've got x to the fourth power, which again is kind of similar to a parabola, but it's kind of flattened down the bottom. And x to the fifth power, and again, notice with these odd powered ones, it's going through -1, -1, and +1, +1 again. And also, notice it's kind of like the cubic, but it's flattened in the middle, just like the fourth power one was a flattened parabola. So what we want to do first here is sketch y equals -x cubed, and we want to use the fact that we know it's a reflection of -x cubed. So remember what this reflection does. It's a reflection over the x-axis. So instead of that point being at 1, 1, where it was right here, it's now down here at -1, -1. And in fact, I think what I'll do is draw a quick sketch here of the original. Maybe a little bit flatter than that. But that's like the original one. So when we reflect it, which is really the important thing that we're getting at here, it's going to come down like this. Go through those values. So you can see it's the reflection. This gets flipped up to there, and this gets flipped down to here. So a reflection over the x-axis. And you can kind of see it there. That's a little better picture, and the graph is a little bit more spread out. The next one, x minus 2 to the 4th power. And again, I think what I'm going to do here is draw a quick sketch of this. The 4th power one, remember, looked very similar to a parabola, but was flattened in the middle. And so the x minus 2 moves that 2 units to the right. So it's now going to be centered over here instead of centered at 0, 0. And again, to take a look at that, we see that there. Notice the center is at 0, or negative 2, comma 0. And then finally, negative 2, x to the 5th plus 4. Again, this is x to the 5th power, which if we thought about that, I'm going to spread these out a little bit. The x to the 5th power was again one of these things that got flattened out quite a bit right around 0, or right around the x-axis. And so when we are looking at transforming this, the first thing is it's a vertical stretch, it's reflected, and then it's moved up by 4. So we want to keep all of those things in mind. Well, this point right here simply moves up 4 spaces. 1, 2, 3, 4, and it's going to be right here. It is a vertical stretch, so it won't be quite as flat, and it's reflected. So it's going to look something like that as it comes through. So again, to take a look at a little better picture on the computer, we can see that it still has been moved up 4 units, it's reflected, and it's a little bit stretched out. So the next thing we want to talk about when we look at polynomials is the leading coefficient test. And this test determines what happens at the ends of polynomials. And the end behavior of a polynomial is determined by looking at 2 things. The first thing is its degree, which is n in that standard form, and also the sign of the leading coefficient, a sub n. So the first thing we want to look at is an odd degree where n is greater than 0. Now first, some notational things. When we see x approaches infinity, so when you see this right here, x's go left and right, so that as x approaches infinity, that means we're going to the right. When you see x approaches negative infinity, again, x's go left and right, so going in the negative direction forever, that's going to the left. But then when you see y approaches infinity, remember y values go up and down. So y approaching infinity means we're going up, and then y approaching negative infinity means we're going down. So it's very important to remember, are we talking about x's or are we talking about y's? So now to look at this particular graph is just kind of a basic graph where it's an odd degree and then the leading coefficient is positive. And you can see the descriptions here. And we'll always have 2 descriptions. The 2 descriptions will be, first of all, as x approaches negative infinity, or as the graph goes to the left, what happens? And then we'll also have, as x approaches positive infinity, or as the graph goes to the right, what will happen? And you can see in this case, this graph is going down, so that's y approaches negative infinity. And on this side, as you go to the right, the graph is going up, so that means y is approaching positive infinity. Looking at this one, it's an odd degree, and this time the leading coefficient is negative. So again, as we're going to the left, we can see this one is going up, so y approaches infinity. As we move the graph further to the right, this is going down, so y approaches negative infinity. And there's nothing magical about this. This is just properties of what happens when it's an odd degree and a negative leading coefficient. So now we're looking at an even degree, and the leading coefficient is positive. As we look at this one again, as x approaches negative infinity, as we're looking to the left on this graph, we can see this graph is going up, so y approaches infinity. And in this case, even as we go to the right, the graph is going up, so y is approaching infinity again. The thing that I kind of do with the even degrees is they kind of resemble parabolas. So if we think about a parabola that has a leading coefficient that's positive, it opens upward at both ends. And that happens with any even degree polynomial. And then finally, just like a parabola with a negative leading coefficient, as this graph goes to the left, it's going down, so y approaches negative infinity. And as you go to the right, this graph is going down, so y approaches negative infinity. So now we need to talk about describing the end behavior. So looking at this first one, the only two things we look at are what is the degree and is the leading coefficient positive or negative. So first of all, the degree is even because it's a 4. The leading coefficient is negative 2. So what that tells us is, because the degree is even, it kind of acts like a parabola as you go to the left and to the right. And since the leading coefficient is negative, that means the graph is opening down. So we would say as x approaches negative infinity, and remember that means as you go to the left, y approaches negative infinity, that means it goes down. And also as x approaches positive infinity, as it goes to the right, y approaches, oops, that's not right, y approaches negative infinity again, because it's going the same direction, because just like a parabola, that's what's happening. So for example 3, again we look at two things. Our degree is odd, our leading coefficient is positive. Now when the degree is odd, the left and right sides are going to be going opposite directions. One will go up and one will go down. When the leading coefficient here is positive, the way I think about this is like a line with a positive slope. The left side is down and the right side is up. So, again to describe it, as x approaches negative infinity, as we look to the left on the graph, y approaches negative infinity. It's going down. And as x approaches positive infinity, as we look to the right on the graph, y also approaches positive infinity. Okay? And then finally, for b here, again we look at the leading the degree and the leading coefficient. Well, notice these are the same. So there's no additional work to do. The answer will also be the same. All that other stuff that's after the leading coefficient and the first term, that doesn't affect the end behavior. It affects the stuff that's all in the middle, but it does not affect the end behavior. Now when we talk about polynomials, many times they have real zeros. And a real zero of a polynomial is defined like this, or stated like this. If p is a polynomial and c is any real number, then the following statements are all equivalent. So saying any of these things is really saying the same thing. First of all, you could say that c is a zero of p. So if we call something a zero, that's one way of saying it. Next, we could say that x equals c is a solution to the equation p of x equals 0. So we can sometimes call them solutions. We can say x minus c is a factor of p of x. And we'll kind of see that later on as we do some of these examples. We can say x equals c is an intercept of the graph, is an x-intercept of the graph of p. So looking at those, we've got several different ways. We can talk about c being a 0. We can say that c is an x-intercept. We can say that c is a solution. And then more specifically, when we're just doing the algebra of it, we can say that x minus c is a factor. So now the intermediate value theorem is something that's very important with polynomials, and it's actually how our calculators are programmed to find solutions. And here's what it states. If p is a polynomial function and p of a and p of b have opposite signs, then there exists at least one value c between a and b for which p of c equals 0. Here's what that statement means as we think about the x-axis here. This is saying that if you've got an a value and you've got a b value wherever they are, and let's say p of a and p of b have opposite signs. So let's just say that this one's up here. So this is p of a, this is p of b. They have opposite signs. P of a is positive, p of b is negative. Well, since polynomials are continuous, you know, they make all these curves or whatever they do. Whoops. What they're saying is, at some point in this region between A and B, basically the graph has to cross the x-axis. In this case, it's right here. And they're calling that point C. They're saying somewhere there's a C value between A and B so that P of C is equal to 0. And that's all they're saying. They're saying that it can't jump over the line. Now, we know that with a polynomial, since they're not straight lines, this could actually come down and hit this a whole bunch of times and still go through B. But all we're saying is that there is at least one value in there so that that's true. So that's the intermediate value theorem. Very important theorem for us. So now we want to try some guidelines for graphing polynomial functions. First thing we want to do is, if we can, factor the polynomial to find its real zeros. Then we want to determine the end behavior using the rules we just learned with the leading coefficient test. Then we want to make a quick table with some x values, a quick t-chart, in between the zeros so we get an idea of what's going on in between those zeros. And then the final thing, plot the points and connect them with smooth curves because we know that polynomials are always formed of smooth curves. There's no pointed or jagged spots on them. So let's take a look at some of these, and I put a grid on here just to make it a little bit easier to graph. So let's start out with what we know. Since we have x plus 2 as a factor, that means x plus 2 could equal 0, which means x equals negative 2. In this case, x minus 1 equals 0, so x would equal 1. In this case, x minus 3 equals 0, so x would equal 3. So that gives us some points to plot. We can plot a 0 at negative 2, we can plot a 0 at positive 1, and we can plot a 0 at x equals 3. So that's the first two steps. It was already factored for us, and then we found the zeros. Next, we want to make a quick t-chart. So let's put some values in between here. Oh wait, I skipped a step. We want to talk about the end behavior. Well, if we look at this, x times x times x is going to give us the leading coefficient. And x times x times x would give us 1x cubed. So what that tells us is odd degree, positive leading coefficient, it's like a line with a positive slope. So let's go ahead and put that in here. That means after we go through this, it's going to be going up, and after we go through at negative 2, it's going to be going down. We don't know yet what happens in between. So now let's make our t-chart. Let's try just a couple values. Let's go with negative 1, 0 is usually pretty easy, and 2. So we don't have to do tons of values, but just a few. So looking at this, if we plug in a negative 1, we have negative 1 plus 2 is 1, negative 1 minus 1 is negative 2, and negative 1 minus 3 is negative 4. So that's going to give us 8. When we plug in a 0, we get 2 times negative 1 times negative 3, and that gives us 6. And when we plug in a 2, we get 4 times 1 times negative 1, which gives us negative 4. And I'm just plugging that in, the x values in right here for this x, and this x. So now let's go ahead and graph this. We've got negative 1, 8, which would be right up here, 0, 6, and 2, negative 4. So as we look at this, we can come down here and at least get a pretty good idea of what is going on with our graph. Okay, so that's kind of what we came up with for our graph. The actual picture is going to look like this. And so you can see we're pretty close on what we've got. I've stretched it out a little bit differently than this one is, but that's the idea with our graph. Okay, the next one here, we have to do some factoring first. So the first thing we would do is factor out an x, and then what's left is x squared minus 2x minus 3. And then we can factor again using the rules that we know. We break it up into two parentheses, an x and an x. We know the signs are different, and then they have to multiply to be negative 3 and add up to be negative 2. So it's got to be a negative 3 and a positive 1. Now again, looking at our zeros, this one gives us a 0 of 0. This one gives us a 0 of x equals negative 1. This one gives us a 0 of x equals 3. So let's go ahead and put those points on our graph. 0, negative 1, and 3. Then, as far as end behavior, if you look back at what we had here, it's the same as the last one. It's an odd degree, positive leading coefficient. So again, we know on this side it's going to be going up, and on this side it's going to be going down. So now let's do our t-chart. And let's pick some values. This time we're going to have to use a fraction, so negative 1/2, because we want something in between those two zeros, and then maybe 1 and 2. So if we put in negative 1/2, we're going to have, I'm going to use this version of it right here. So negative 1/2 would be negative 1/2 times positive 1/2 times negative 3 1/2. So that would give us, this is what? 7 halves, negative 7 halves. Use that. So that gives us positive 7 over 8. So 7/8, and we'll put that in there in a little bit. If we put in a 1, we'll have 1 times 2 times negative 2, so that's negative 4. And if we put in a 2, we'll have 2 times 3 times negative 1, which is negative 6. So graphing these, we get the 7/8, which is about right here. We get 1, negative 4, which is here, 2, negative 6, which is here. So again, we're just getting an estimate here. It's going to come through there and up through there, and we can see how that works. To get a little better picture, okay, you can see that same idea. Here's our 7/8 that we put in up here. Here's the negative 6. So we can see all those values pretty nicely. Now in this one, as we look at it, notice we can factor out some things. We can actually factor out a negative x squared. And that leaves us with 2x squared minus x, plus x minus 3. So now this is that little longer process. We have to take a times c, so 2 times negative 3 is negative 6. And find factors of negative 6 that add up to be positive 1. They have different signs, so it's going to be a positive 3 and a negative 2. So when we factor this, we've got negative x squared times, and then we've got 2x squared minus 2x plus 3x minus 3. And notice we can factor each of those by grouping. So negative x squared, we factor out a 2x, and we have x minus 1 left over. We factor out a 3, and we have x minus 1 left over. So negative x squared times 2x plus 3 times x minus 1. Now this one's maybe a little trickier, but we again get x equals 0 and x equals 1. This one, it's 2 steps to solve it. We subtract 3 and divide by 2, so we get negative 1.5. So those are the zeros that we've got. 1, 0, negative 1.5. Then if we check the end behavior, notice what happens here. It's a degree of 4 that's even and a negative leading coefficient. So we actually know that these are both going down once they get done hitting their zeros. So now let's make our t-chart. And I think probably 2 points is going to be good enough. I would try negative 1, and I would try 1/2. So if we put in a negative 1, we get negative 1 squared. Negative 2, or 2 times negative 1 plus 3 is 1, and negative 1 minus 1 is negative 2. So notice that's just a 1. This ends up being 2, so that's not bad. The other one might be a little trickier. I'm going to do this work down here. So negative 1/2 squared is negative 1/4 times 2 times 1/2 is 1 plus 3 is 4, and then 1/2 times, or 1/2 minus 1 is negative 1/2. So notice the negatives will cancel out, the 4 and the 1/4 will cancel out, and we get 1/2. So here's what our picture is going to look like here. We'll have negative 1, 2, and then we'll have 1, 1/2. So notice what happens. This comes down and just touches, and then comes back up, and then goes down through that 0. There's actually a reason for this happening, and it's because that 0 has a multiplicity of 2 because it is a power of 2 there. That 0 happens twice. So there's a little better picture of it so you can see it. And again, we've got the main points there, a little different scale, but that's our graph. All right, looking at this one, we've got 4 terms. And in this case, we've got to use something that we have talked about before called factoring by grouping. So notice we can factor x squared out of the first 2. We try factoring by grouping anytime there's an even number of terms. So we'll have x minus 2 left over. And then in the second one, we can factor out a negative 4, and we'll have x minus 2 left over again. So that's x squared minus 4 times x minus 2. And then remember, we can factor x squared minus 4. That's the difference of squares. So x minus 2, x plus 2, and x minus 2 again. So our zeros, x equals 2, x equals negative 2, and x equals 2 again. So notice here again, we've got this multiplicity issue. It has a multiplicity of 2. So we've got a 0 there, and we've got a 0 here at negative 2. Checking out the leading coefficient test, it's negative, or sorry, it's odd and positive, so it's going to be going up to the right and down to the left. And then again, to put some points in there, we don't need tons of them, but let's go with negative 1, 0, and positive 1. So if we put in a negative 1, we get negative 3 times 1 times negative 3, so that is 9. If we put in a 0, we get negative 2 times 2 times negative 2. That's 8. And if we put in a 1, we get negative 1 times 3 times negative 1, which is 3. So graphing these points, we get 9, 0, 8, and 1, 3. So looking at what happens here, this comes up and then back down. And notice, whoops, I missed my dot there, I couldn't see it. Notice it actually comes down and bounces off of there and then goes back up. So that's a look at our graph. Again, the multiplicity of 2 causes this to just come down and touch the x-axis at that point. So there's a little bit nicer picture. Now we've kind of discovered some properties about multiplicity, and here's the description of it. The shape of a graph near zero depends on the multiplicity of the zero of the function. The multiplicity, again, just means how many times that zero occurs. So for odd multiplicities greater than 1, they resemble cubic functions near zero. So they have that little S-curve shape, as you can see right here. Kind of an S-curve. For multiplicities that are even and greater than 1, they have this shape like a parabola, just coming down and touching the x-axis at those points. So those are our two characteristics. We're going to use them here in this last one. Notice it's already graphed, it's already factored for us. So if we identify the zeros first of all, we've got x equals 0. Notice that's a multiplicity of 4. Got x equals 2, that's a multiplicity of 3. And x equals negative 1, that's a multiplicity of 2. So let's put the zeros on here. 0, 2, negative 1. So as we think about in behavior, we just want to look at what happens here. We've got x to the 4th times x cubed times x squared. So we can see that's going to be 1x to the 9th power. So it is an odd degree and a positive leading coefficient. Notice what happens. Since this one has a multiplicity here of 2, it's going to be going down after this, but remember it just comes down and touches it kind of like a parabola shape. So it is going down, but it doesn't go through the x-axis there. At 0, the same thing happens, but it's even more flattened out. And then, once you get up to 2, notice it's an odd, so it's got kind of this cubic shape. And remember, it was going to go up there. Now, that's not exactly right, but again, this exercise is mainly to get the idea of what happens close to 0. So now we'll show you the real graph. Mostly negative. This obviously goes down a lot further than I had it going down. But you can see the idea. Right here we have kind of the parabola shape. This one is a 4th degree, so it's a little flatter, but still that parabola type shape. And then we've got the cubic shape at the end. So finally we get to local extrema of polynomials, and we're looking at this general form of a polynomial again. And this is a polynomial degree n. The graph of p has at most n minus 1 local extrema, or extreme values. So for instance, if your degree was 5, it could have at most 5 minus 1, or 4 extreme values. I'm going to take a look at this using the graphing calculator, and then we'll come back afterwards. So as we look at example 9 here, we're going to be looking at how many local extrema each polynomial has. So the first thing we need to do is we want to go to the y equals, and we want to enter in our points, or our equations. So we have x raised to the 4th power plus x raised to the 3rd power minus 16x squared minus 4x plus 48. Then to take a look at that, we want to go to the graph screen. And we know since the degree is 4, it can have at most 3 local extrema. So it looks like there's probably one in this area. There's going to be one up here out of the screen, and then probably another one down here. So we're going to have to adjust our picture a little bit. So we're going to go to Window. Notice we don't need all this X stuff on the outside. So let's just go from a negative 6 to positive 5. And for the Y value, I'm going to have to guess a little bit. I would say maybe negative 15. And that one seemed pretty high, so we'll say 50. Let's see what that does. And then our scale, we'll just go by 5s. So if we hit graph again, okay, we're still not getting that one. We have the top one. So we're going to have to adjust a little bit lower than negative 15. So go to our window again, go down to that negative 15, and let's make it negative 25. See if that gets it for us. Still not quite, but we can see it's definitely right there. We don't even need to find them specifically, it's just that there are 3 of them. So clearing that off and going to B, we've got x raised to the 5th power plus 3x raised to the 4th power minus 5x raised to the 3rd power minus 15x squared plus 4x minus 15. Now I'm just going to take a look at where my window is already and see what I need to do to make any adjustments. It looks like basically I need to move my screen down. So I'm going to go to Window. Looks like the x values are okay, but my y values need to be significantly lower. So let's go from negative 50 to 0. Okay, notice we have a maximum value here, top of that hill, a valley here, so that's a minimum. Another hilltop there, so that's a maximum, and a valley there is a minimum. So we get 4 for our number of relative local extreme values. Then our last one, part C, we have 7x raised to the 4th power plus 3x squared minus 10x. And again, if we graph that, we're not seeing a whole lot right now. Let's go back and zoom to our normal window. Zoom 6 brings us back to that standard screen from negative 10 to positive 10. Okay, and not totally sure here, but let's alter our window a little bit. I think our x values are fine, but our y value possibly up higher. So let's go up to, 100. And I'm going to shrink this a little bit, negative 5, positive 5. So as we look at this, okay, we can see pretty confidently there's only one minimum there, and it's a relative minimum, or a local minimum. And so that's the answer to part C, is that there's just one minimum value there. So we saw there were 3 extreme values in A, 4 in B, and then just 1 in example C. So the assignment for tonight is there. You'll have time to work on that again tomorrow, but for section 4.1, it's pages 322 and 323.